Okay, great. Welcome everyone. This is another fun session with friends all around the world and around the country. My name is George, and I'm joined today by my great friends Robert and David, as well as some new great friends and existing friends like Dimitri, Joseph, Mike, Chuba, and Laura, and everyone who's watching us online. Thank you so much. Hopefully one day you can attend a live session. If not, feel free to comment on YouTube. That's where we post all our sessions, as well as on social media. Today we're continuing our deep dive, I would say, in TensorFlow, specifically TensorFlow data sets, the different APIs. How do we read data from different formats, and how do we prepare it in an efficient way so that we can feed that data into a neural network, a model that can make probably regression task or classification task and so forth. Let me start sharing my screen so I can give a little bit more context of what we do. So again, you can find us on Meetup if you search for Deep Learning Adventures. We've been pretty busy with this new specialization, relatively new to us, called Data and Deployment. And we've covered so far 2 courses. We're in the middle of a 3rd course, which is content-packed. And today, Robert and Dimitri are going to cover some great material from course 3, week 3, as well as some other notebooks that are there in the tutorial section of TensorFlow. We have another session for next week, for week 4, and then we're going to conclude this course 3 journey with a happy hour, a much-deserved happy hour, as you mentioned, Robert, before we go to course 4. Just to pay attribution where it is due, some of the links and some of the content you're going to see today, or most of it is edited and is created by Coursera and Deep Learning AI. I want to thank them for their awesome work of creating this content and sharing it with the rest of the world so that all of us can sharpen our AI skills. Cool. With that said, I want to keep it short. I know we have a lot of content to cover, so I'm going to hand it over to Robert for a deeper dive or continuation of week 3.
Good evening, everyone. Can you see my screen?
Yes, ETL revisited.
Got it. So I won't bother to maximize this. We're just going to remind ourselves of the concepts that we've been covering so far in this course. And the real objective here is to master TensorFlow. We really need to understand the various input mechanisms available to us and the typical process that one follows to get data from some other place to the point that it's loaded into a TensorFlow model is called ETL, extract, transform, load. Many of you in this business may be familiar with that paradigm already, but to talk about how it applies to TensorFlow, typically we will have data that we want to use to train a model. That data could come from a variety of places. TensorFlow data sets, data which is natively built into TensorFlow itself, is one great source of data, particularly for educational material. There's a lot of the most commonly used academic and educational data materials there, including the MNIST data, Fashion MNIST, various other image data such as CFAR, some object detection stuff, COCO. There's a lot of text data there. There's a lot of video, some audio. There's a lot of different data sets at TensorFlow datasets. So that is one place that we could be extracting data from. We could also be attempting to use our own data. Maybe we're reading it from a file. Maybe we're reading it from a directory containing a ton of files. Maybe we're reading it from some other source that has prepared data in a TF-friendly format. Tonight we're going to see processes for converting all of these, for extracting data from all of these different sources and then transforming it into a form that can be fed into a model for training. So typically the last step that you'll do, you'll have a data set, you'll transform it a number of times, get it into a certain form, and then the load step of the model is really often just writing it as an argument to the model. A little bit later tonight, we'll be talking about the trade-off between the CPU and GPU. And one thing that happens when you train a model is you want to be able to use both of your devices as well as you can. You have a CPU, which is optimal at certain tasks. CPU can run sequential tasks very, very, very rapidly. A GPU is great for parallelization of tasks that can be run in parallel and don't necessarily need to be executed quite as quickly, each individual task, because they've been parallelized. So certain parts of your process lend themselves better to the CPU versus the GPU. We'll talk more about that. But at a very high level, we're really looking at pre-processing, which is typically reading your data in, doing the the extract, and the transform part, and the E and the T typically are pre-processing. And then when we talk about loading into a model and doing model training, that is typically the most parallelizable part of the process. So at that point, we want to be on the GPU. So what we would like to do, we have this task here. We're preparing data on the CPU, and we are training data on the GPU. And this is a visual from the course, and it gives a nice idea of some of the design considerations that we might run across in these tasks. If we prepare our data here, train it there, prepare another batch of data here, train that batch here, prepare another batch 3 here, train that batch here, there's a lot of idle time in between. So is there a way that we can maybe use our devices a little bit more efficiently? And if we're smart about the process, we can. There's some strategies that you can take with data pipelines, a lot of mechanisms that are built directly into TensorFlow. And you can see how, even though each of these tasks takes the same amount of time, by doing it smartly, you can save time overall. Once you've prepared batch 1, you can simultaneously train batch 1 on the GPU while preparing the next batch on the CPU. So this part about optimization, performance optimization, Dimitri will be covering in detail tonight, but I wanted to give a very brief overview before I return now back to the E and the T part of the process, just to reorient ourselves to where we were last time in week 3. Any general questions before we move on?
Perfect. I thought we were covering week 4, and I was like, I don't think we're done week 3 yet.
Well, we're doing the last notebook from week 3, but the material that Dimitri is presenting it's a separate notebook in TensorFlow guide, but it really corresponds to week 4.
Perfect. Awesome.
The front half of week 4. Week 4, for anyone familiar with the course, you'll see it's divided into a performance optimization part and a data set publishing part. The data set publishing part is now optional. We'll be going over that next week here, June 30th. So that'll be another fun session. I'm also hoping that we can, let me see if I can move this screen down so that I can actually get to I always find challenging to navigate around Chrome here when I've got the Zoom window blocking me at the top. Okay, so TF data here, the notebook that I'll be covering is on this TensorFlow guide tensorflow.org/guide/data, and there's 3 units on data input pipelines. TF data here is a notebook that is provided with the course, and it's also obviously at this URL, and it's the same notebook. I've modified it a little bit and added some test cases, just explored it a little bit, but we're going to step through it pretty quickly. We started it last week. We had some general discussion on the very first section, so I'm hoping that we go through, we'll remind ourselves of that, but we won't spend a ton of time there. Dimitri will be talking about the Optimized Pipeline Performance notebook here, the second one. And I'm hoping that next week one of us can cover this Analyze Pipeline Performance notebook, which is not technically part of week 4, but it looks pretty interesting too.
Awesome.
So let's see, that being said, what I did is, one of the cool things about TensorFlow is you can download the notebook, you can view the source on GitHub, or you can run it in Google Colab. So if you click run on Google Colab, you can get your own copy and save it to your own Google Drive here. And then you can start to not only run the code that they have, but you can add your own cells and experiment to start really finding out within the confines of this IPython notebook, just understanding the whole process. So the table of contents of this notebook, I'll probably close it here eventually because it takes up a good amount of space on the screen. But just so that we know in advance, last week what we covered in detail was basic mechanics and dataset structure. I'll run down through that quickly for review. Then we'll go down through reading input data. As you see here, this is just a bunch of different use cases, consuming data from Numpy arrays, consuming from Python generators, TF record, format, text data files, CSV data, sets of files. And then we'll start talking about transformations, how to batch dataset elements, some interesting things about batching. We'll talk about training workflows, processing epochs, randomly shuffling the data, shuffling and repeat transformations we'll go over there. Then at the bottom, there's a lot of other pre-processing that we'll really mostly skip over. There's some really useful stuff here though, and I do encourage you to check it out if it's relevant to your own projects. Let me rerun the whole notebook. I think it's very quick. So we start by importing TensorFlow, importing our familiar packages. Basic mechanics, we're starting with a data source. There's a couple different ways, but the simplest way to build tensors is with this from tensor slices that we saw last week. And there's a distinction between that and from tensors. As we saw last week, from tensors is a very uncommon way of doing things because you only get one element in your data set. It just assumes that instead of returning different records, you just want this whole array to be a single record, single element. From tensor slices takes this 5x2 array that's coming in, and what it's going to do is it slices out the first dimension, so you end up with 5 samples, and then when you take from these 5 samples, each one of them is an array of 2 elements. So just showing some examples there we walked through last time. Tensor slices, regular tensor data sets, the reduced transformation here. Again, that's in the video from last time. We went into this in some pretty good detail, so check out last week's video, which has a lot of this content. One thing that we saw is that an element that's returned it's a very complex structure we can have. We don't have to just return arrays of a regular shape. We can return things that are zipped, tuples of totally different objects. Here we're returning something that is a tuple of a 10 vector here, and then 2 different objects on the other half of the tuple down here. And the same types of Python access operations can be performed here with the take operation as in base Python. There's a number of dataset types that we uncovered: tensor slice dataset, zip dataset, tensor dataset. These are all representations of different transformations and not necessarily new positions for elements of the data in memory. So we showed a little bit of the source code for some of this stuff last time. We walked through that example. So when we talk about different input sources, let me ask if there's anything we should discuss before we move on to the new material.
Well, this is a great review. Thank you for going over it again.
Excellent.
Yeah, feel free to post any questions in the chat or unmute yourself in the meantime.
Yeah, I won't always see the questions in the chat, but I trust that George and David will monitor that,
Yep.
and we'll get
Got
questions
you.
answered as needed.
Yep, we got you. Don't worry.
So the first example here was consuming NumPy arrays. We have, remember, 6 examples to go through: NumPy, Python generators, TF record, text, CSV, sets of examples for the E part, the extract part. And NumPy is probably the simplest one to work with because they're natively just straight arrays. And in this case, it's as simple as calling a single command here, fashion mnist load data. This is the, I don't have a link to it up, but we've seen this data set before a number of times. Fashion mnist is 10 different types of fashion items. You're asking your model to classify: is this a coat, is this a shoe, a pair of pants, a shirt, handbag. I think there's 5 other items. So it's analogous to the most famous data set mnist, which is handwritten digits, where there's also 10 items to classify. You want to know if it's a 0, a 1, a 2, etc. that the person wrote. So you're looking at images of all of those. So typically when we're working with NumPy arrays, we'll use the from tensor slices because we're given these things in an array. We have the fashion mnist data set will have 60,000 images, and each of these images is very small, just like mnist. It's 28 pixels by 28 pixels, so it's only 28 by 28 horizontal by vertical. And these are 60,000 labels. It just tells us which element of the data set, or what is the truth type of that, for each of the 60,000 examples. And when we run a from tensor slices, what it does is it slices off that first dimension, turns them into examples. And so each element returned by this data extraction process is going to be a 28 by 28 image. And this little pair of parentheses here just tells us that the second element returned is a scalar. So it doesn't need to mention the shape because it's just one number.
It's interesting that the data type of train D type was int, but then when you convert it to data set, it became float.
Is that right?
Yeah. So 27 and 28. So.
Well, I think what happened here was this.
Oh yeah. Sure. I missed that part. Okay, cool.
All right. So just showing another example. I think this one, if you don't have one of the things, because you're slicing the first dimension, you want to make sure that the number of elements matches. We have an array with 37 by 10, 37 by 3. We can slice that one just fine and return elements of size 10, elements of size 3. But if we try to combine a 37 with a 35, we'll trigger an exception here, and we'll get dimensions 37 and 35 are not compatible. And once we have these dataset objects, as we've seen in past weeks, we can feed those into a model.fit operation, and TensorFlow will run the model from a dataset object as the input. It will iterate through the data set, maybe shuffle it depending on the transformations that you've defined. Another example they give here is Python generators. Now the first one is very much a contrived example just to to get you a little bit familiar with the concept. I don't think you would ever actually use this one in practice. But the first few cells here are just to initiate you to generators in Python, if you're not familiar with that. It's very similar to a Python function, with the difference being that instead of returning a value, it yields a value. And so what that does is it preserves the state of the function so that you can then call the iterator again, and it's as if you're just starting right there where it left off. If it had been a return, it would have cut the function, and then when you start again, it's going to start from 0. But here you can say count 5, print n, it's going to yield the number immediately, and then it's going to continue to remember where it was and increment up further. One thing they do mention here is that generators can be convenient for certain tasks. We'll see one here in a minute. But it has very limited portability and scalability, so it's not used too often. It's subject to the Python global interpreter lock here, so it has to run in the same process that created it. So if you want to parallelize your processing, generators are generally not going to be very compatible with that.
So it's almost like a state machine, right? You remember the last state and it continues from where it left.
Yeah, it can be a really useful construct in Python for some reasons. You can create iterators without necessarily having to keep an entire list in memory.
Yeah.
Is Python like strong enough? Like, aren't you afraid of like infinite loops, like where like the count function might like take too long to process? Am I making sense? Like,
It certainly could happen if you have a poorly defined generator.
okay.
This one here is, yeah, I mean it's just like writing any loop. You want to make sure that it's not an infinite loop. In this case, it actually, I guess it is an infinite loop, but you give it, it would be an infinite loop if you didn't give it a stop criterion here.
Right, yeah.
The other thing with generators is you can make them infinite loops, because as long as you're continuing to yield something, it's going to stop each time it yields. So a very classic example of generators might be you might write a code to generate prime numbers. And so then the first thing it spits out is 2, 3, 5, 7, 11.
Right.
And every time it yields, it kicks out of the generator. So your stopping criterion doesn't have to be in the generator itself. Maybe it's somewhere else in your code. Stop printing prime numbers once you're greater than 1,000 or something.
Of course.
So the from generator constructor is what we're going to do here to get our Python generator to become a tf.data.dataset. And one thing to note is that the constructor takes the callable as the input, not the iterator. This allows it to restart the generator when it reaches the end. And what do I mean by callable versus iterator? There is an example down here, but I think the basic example here is that the word count is the callable. It's just the name of the function, whereas the iterator is count after being instantiated with an argument. So once you have an iterator, count 5, it can only be run once. But if you're just referring to the function name itself, you can always just kick up another copy once you've reached the end of it. So when you're using this from generator method, you want to throw the count argument here. And that's pretty cool. They have just an args, so no matter what the signature of the function you're trying to use is, you can throw in args. I don't know if it takes keyword args. It probably does. I didn't look that one up. I suppose one could. And the example they give here uses output types and output shapes. And we'll see that in a little bit. But let's look at an example of what actually happens for, we're going to take this DS counter. We've just instantiated a data, we're going to generate a data set from a generator. And it's just using a counter, and we're feeding it the argument of 25, which is the equivalent of calling this count function with 25 as the argument. And then we're going to batch it in 10. We haven't talked about batching yet, but that's just going to put it in groups of 10. And then we're going to take 10 batches. And when we run this repeat here, we get the first batch of 10 counts up to 0 to 9. And then we get the next batch of 10. And then you'll see that this one actually wraps around, right? It reaches the end of the generator, and it knows, well, I can just start again. So this will, because you gave it repeat without an argument, repeat without an argument is infinite repetition. It will keep, this is an infinite process that will only terminate here because we've given this a finite number. We're only going to take 10 batches. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 batches there. So they talk about output shapes and output types, and this was presented in the course, but we should note that, and I added this to the notebook, this wasn't here, these arguments have been deprecated already. Now they are recommending that you use a method called output signature instead. And why might you need to tell TensorFlow what the signature of the output is? Output shapes, let's see, output shapes is just telling it to expect scalars, telling it to, in this case, it's expecting scalars, and then it's going to batch them into tens. But here we're going to see an example of a data set that, or a generator rather, that can generate differently shaped elements. So the output shapes and output types will, you can't set those. You're going to have to set them to none, which tells it that you don't know what the shape's going to be. And why does this generator yield series of different lengths? It's because it's choosing a random number here from 0 to 10, and then it's yielding an array that's the size is determined on that random number. So when we gen series here, we're going to get a series here with 6 elements, but then we get one with 0 elements here, and it can be anywhere up to 9. And then if we wanted to try a data set from generator here, we would have to set the output shapes to none here, which indicates the uncertainty in the fact that it's not going to produce the same shaped output each time. Now, if this is a problem for your model, and it often is, and we can think of examples where you might want to have the same number of elements being produced, you want to have the same shape vector being fed into your model, no matter what the input was. One great example is text, where you might be working with sentences and tokenization and embeddings, and you want to make sure that the length of the sequence is the same from one example to the next, in spite of the fact that one sentence may be 5 words long and the other sentence may be 10 words long. So in this case, you can use something called padded batch, and padded batch will force the batch to be 10 long. Let's see, this one. Right, so what we've done here is we've printed one, let's see, we printed the IDs of the next iteration, but then if we print sequence batch, some of these are the IDs, batch number 17, batch number 16, batch number 2, but these batches may have different lengths. Batch number 16 here, the second one, is actually empty. And so by padding it, you're going to put zeros in. So one thing to note here is that we gave it a padded batch of 10, but if you're going to just look at a sequence batch within such a generator, you might actually have a sequence of batches that doesn't have any examples of the maximum, right? The longest batch in here was 6 long. So in order to be safe about that, you may have to redefine some of the code up here to make sure that you're yielding a padded batch of the correct size.
Is that because the first batch of 10 elements only had the maximum length of 6? What if the next batch had 7 or 10?
Yeah, so it's gonna choose. So here it just chose to give you a NumPy array where the width of that array is defined as the maximum of whichever of these vectors that these indices point to is. So maybe this wasn't the I think
I was thinking if you run those commands again, idea sequence batch print, you might get a longer
sure
one.
we can do
last
that.
few, just the last 4 commands.
Well, I'll change the seed. Maybe we'll get something different. I think I played around with these 3 seeds here while I was looking for examples, and all of them, this one TF random set seed, NumPy random seed, and the shuffling seed itself.
Mm-hmm.
You have to fix all 3 of those to get reproducible results.
Oh, I see.
If any one of them is not, then this will give varying results. So I'm still not totally sure every time I use seeds whether it's going to function as I think.
Got it. No problem.
So let's try different.
No, but I'm saying if you try different seeds or different, if you try the cell again, it will behave similar. It will have different length. I'm just saying run those last few commands again somewhere else. Yeah.
You want to open up another cell?
Yeah. So that way you still have the batch 10, but you're taking another.
So here we have some of the same elements again, or are they the same elements? 16 was empty.
Yep.
But 17, maybe they're random within. I don't remember.
Got it. But now the length is different. It's 8. So
yeah, the length is different because it had a longer one that it had to accommodate.
So it figures out the maximum length within that batch.
But this could be a problem for you if you're giving different batches and you want to, in maybe one part of your process, you may want to have a maximum batch length.
Sure. Yeah.
So moving on to a little bit more realistic example where you'd actually want to use generators. This was a very contrived example, although it bears some similarities to text processing. This is using image data generators, and we've gone over this, I guess, in the convolutional neural networks class. So I won't really go into this too much, but what happens here at a high level is you have a bunch of images in this directory on your hard drive, flower photos, and there are 5 different types of flowers: daisy, dandelion, roses, sunflowers, and tulips, and you're going to try to classify those flowers. Now these are directories, and the file structure is organized. There are JPEG images inside the daisy directory of daisies, JPEG images inside the dandelion directory of dandelion, etc. So once you have your file system organized in this way, TensorFlow has these commands, the image data generator and the generator.flow from directory, which enable very easy ingestion of this data. So you can train a model very easily with just this couple lines of code. You've loaded your data already. The third example they give is TF record data. So the links in the existing Colab, there are a lot of broken links. Just wanted to point that out. You can see, I guess, if you look at the URL that it points to comes up when you hover over it. There's a tutorials load data TF record, and then this one goes to a much longer URL. I guess you can't see the whole. There it is.
Yeah.
But it still ends with tutorials load data TF record, but now it's pointing to the TensorFlow GitHub site. You'll have to make similar changes if you wanted to fix all these links. It looks like Google has not done that yet. I guess. So I didn't fix most of the links, but just thought I'd point that out. Here they use an example from the French street name signs dataset, and the TF record file format is reading your data in what they're calling a record-oriented binary format. So you have to have some kind of a parser to figure out where your images are within that stream, where your labels are within that stream, and the TF record dataset class enables you to stream these things as part of an input pipeline. And this can help with parallelization as well, because you can have shards, many different shard files, and you can send them all to different places. So this notebook here, TensorFlow Tutorials Load Data TF Record, goes into detail on how this works exactly. The course described it a little bit. I'm not going to touch on it further. We also have consuming text data. There was a little bit of interest in this example. Here we have three different versions, I guess three different translations of the Iliad, which is Homer's Iliad. Was it Homer? I think. Three different translations by Cowper, Derby, and Butler. And let's just look at a few lines of the first file. So these are byte strings. And they show this example just to demonstrate that if you want to alternate, grab lines from one file, different files, you can use this command Dataset Interleave. That way you can shuffle files together. So now you're looking at the three files, first line of all three, second line of all three, third line of all three. Depending on what you're doing with your text data set, that could be useful. You can also remove header lines with the skip, and you can even do some filtering, almost like Excel style filtering here in the example they show. Here they're going to look at a CSV file, but they're going to treat it as if it's text. So what you're looking at is just the comma separated line of text. And this is the Titanic Data Set, yet another famous data set in the world of machine learning. And this one is often used in educational settings where you're learning models and you're trying to predict based on the demographic and some other characteristics of people who were on board the fated Titanic voyage, ill-fated Titanic voyage, whether or not they survived, whether or not they died at sea or not. So 0 is perished and 1 is survived. And what they're doing here is just showing an example of how you might use the filter command. You can filter the lines based on how they survived using this tf helper function here.
So you're reading the entire row as text, basically. You're not delimiting it by anything.
Well, you're reading the entire row as text, but then this substring here is only looking at the first character, right? Character starting at 0 and ending at 1.
Got it.
And then just checking, is it a 0?
Yeah.
Or checking not equal to 0. So it's really just looking for the ones.
Okay, sure.
So you get these passengers here as the first 10 that survived. So you can do the survivors.take10 after doing this transformation with the filter.
Yeah, so Laura's asking a question, is this classification? Yeah, so here you only have a specific number of classes, true or false, or 0 or 1. And the goal is to build a model that looks at different features, based on like age, sex, which station they boarded on, and different other things. And the goal is to predict if they survived or not. So whatever your target is. So in your example, it'd be something else. Yep, that's classification.
Yeah, it's a binary classification is when you have only two options, true or false. So then they go on and show how you might load your data in from CSV files. CSVs, this is another example of the Titanic. We're just getting it a different way now, using this Keras utils.get file. Won't really go into that. There's some information here about how to read sets of CSV files and large CSV files where you may have to send them multiple places. There is a little bit here about how you might treat CSVs with missing data. So you can do this map function here, which is a transformation. And you've I guess the experimental CSV data set is writing in the default values. So whenever there's a missing one, it throws a 999 in.
Oh, interesting.
Yeah. And then the last input example was consuming sets of files. Datasets distributed sets of files. We've seen this already. This is the example with the images in the directories. I don't think it's substantially different here. They go into the tf.io operations. So a very quick overview of some common transformations in TensorFlow. Batching is really critical. So you're going to have a data set that hasn't been batched is typically yielding elements one at a time. One record of your data set, one row of a data frame, one image from your image classification task. But for maximum efficiency, you often want to batch them together. You may be training in a way that you only want to take one step of gradient descent every X images, X maybe 32, 64, typically power of 2. And so what the batch transformation is doing is essentially taking n consecutive elements of your data set. You had 32 different things that you were outputting, and now you're going to just drop 32 elements at once every time you take from a batched data set. So a bit of a simple example here. This is a zip data set where we've batched it with 4. So instead of taking just a 0 and 0, 1 and -1, we're now getting 4 elements at a time in each element of the zip. And if we hadn't batched, when we ran a take 4, we would get just one scalar number at a time. And with the original data set, we would have gotten just a tuple at a time. One thing you can do, and this is another example where you have an indeterminate size that's being yielded. So here we're taking a tf fill. What this is going to do is it's going to produce, this is going to be the length of the array, size of the array, and the fill value is 3. So it's going to fill an array that has size 7 with the number 3. Now if we make this more general, and instead of filling 7, now we're going to make it a lambda function of some x, and we're going to feed in some number that may change. now all of a sudden our data set is going to be yielding objects of different size. So if we take 2, we're not going to shuffle in this case, so we're going to get the elements in order. But we're going to have something with 0 elements here, 1 element, 2 elements, and 3 elements. And we're using the padded batch is just going to make sure to pad as long as it needs to be to match the longest one. And then the problem with that, of course, is that the next time we call for more elements, we're going to get a totally different shaped object. So if you have this type of data set that's unpredictable like that, one thing you can do is use this padded batch transformation that we saw further up. We use the padded shapes equals 9, and now we can force every element to be 9 long, even if it otherwise wouldn't have done so.
Cool.
So now we're moving to the training workflows. We're down in this portion. We're going to talk about multiple epochs and a little bit about shuffling and repeating, which are some really common transformations to do along with batching. Processing multiple epochs. There are 2 main ways to process multiple epochs of the same data. One thing you might do is iterate using the repeat transformation. If you use repeat with no arguments, it's just going to repeat it indefinitely. You will have some other criteria likely that terminates, maybe the number of epochs that you choose to run, the steps per epoch, something is... Often you can have a case where you can run this repeat transformation without an argument, and there's some other thing that will terminate. So here we have the Titanic lines. Now, how long was this data set? I don't recall. The Titanic shape is 627 by 10. So it had 10 columns, but there apparently are 627 passengers that we're interested in knowing the survival or not status of. And if we batch that in batch sizes of 128 elements, then 128 does not evenly divide 627. So if we run the repeat, we're actually going to kind of wrap the batches around. And this chart here isn't well labeled, but what it's showing is that the batches are all the same size until the very last one, in spite of the fact that we will have, by the time this is completed, we've done 3 full epochs, I think. Yeah, repeat 3 epochs, and only the last one is short. So it's just wrapped around each one individually by doing repeat and then batch. On the flip side, what happens if you do batch and then repeat? Now we're going to get each batch is clearly separated, and we get a short batch every time that doesn't complete the full 128, every 5th one. So the order of these transformations can be very important. Just some more information on that there. Another thing that one can do is shuffle the data. So we'll look at what happens when you shuffle and repeat. And let's see, I guess one thing, let's talk about this bit right here. So dataset.shuffle, you need to specify a buffer size when you run dataset.shuffle. And the buffer size is a safety that prevents TensorFlow from having to shuffle too many elements, having to buffer too many elements, have too much data in memory. And the trade-off here is that you don't get completely random shuffling. So if you have 600 elements in your Titanic file and your buffer size is 100, the first element that gets selected is only going to be a choice from the first 100. Then the next element that gets selected is going to be a choice from the remaining 99 plus the element 101 that you just added. So you're going to get some shuffling, but generally the elements that started near the beginning are going to remain near the beginning, and those that started near the end are going to remain near the end. So here we're looking at a buffer size of 100, batch size 20, and the first batch therefore cannot contain any elements with an index over 120. We actually don't get any elements with an index over 100, but at each one of these steps we could have gotten up to 120, I guess, if there's 20 elements out here. So a couple examples just to illustrate the relationship between shuffling and repeating. I chose to do a trivial example here just to set the framework for what's going on here. We're going to use a buffer size of 1, which is the equivalent of telling it not to shuffle at all, because the buffer size is only going to be able to choose the next element each time. So we're going to skip, let's see, we have 10 elements in a batch, and we're going to skip 60 batches. So by the time we print elements, we're already on element 600. So the first batch is going to be these 10 in a row, because our buffer size is 1, they're not random. And then these ones, and then we have an incomplete batch here, because it only has 8 remaining elements, and you batched before repeat. And then you return to the beginning and start over again. So if we want to look at that graphically, we could think as a function of batch number, which items, what is the mean item ID in that batch? It's just going to be a, what do you call this, a sawtooth wave or something.
Mm-hmm.
So a slightly more random example, we're going to have a buffer size of 10. So really just choosing elements very much right at that location. You tend to get elements that are very close to those boundaries, but now we can have some elements that hadn't been selected quite yet from previous parts. You're still never going to have one that's more than 10 above the number that you could have had. So the maximum number you could get here is 610. The maximum number, or actually 609, I think. The maximum number you could get here is 610, 611, etc. And you'll see that you pretty much just have the elements near the top. There's a few that reach back a little ways. This 582 actually reached back, if this was 609, 629, 630-ish, then this one actually managed to survive in the queue for about 48 selections before it got pulled. So, for any one element, what's the chance of that happening? Looks like it's about a little less than 1%. So this is a roughly 3 sigma event, just to give you some sense for how good the shuffling, how effective the shuffling might be for a 10 in the batch. And we look at our little plot here, it's telling the same story, a little bit wiggly, but nothing too significant. Now we're going to go to the examples that they had in the notebook, and we're going to use a buffer size of 100, so we're going to have much more randomness. Batch 10, then repeat 2. Batch 10, then repeat 2 means that you're going to have perfect separation between epochs. And so you're going to get the high numbers here, and then you're going to jump back to the low numbers, but now you can be 100 up immediately. And you plot this, and you're just going to get a much noisier looking raise, much noisier looking rise. What happens if you repeat before the shuffle? Now you're going to see a lot of things mixed together. And when we look at the plot here, it's going to, we put the original shuffle then repeat is the blue line, and repeat then shuffle is the orange line.
Clarify for me, repeat, are you repeating what exactly, the pick that you're doing?
So what repeat is doing is it's allowing the epoch to turn over. If you put shuffle before repeat, then when it gets near the end of an epoch, it reduces the buffer size to make sure that at the end of an epoch, it has taken each element exactly once.
Got it.
If you put repeat before shuffle, it will keep, you've gotten close to the end of an epoch. It's not going to shorten the buffer size. It's going to start pulling elements from the next epoch. So you're going to get some, so maybe the small numbered element from the second epoch has occurred 2 times before one of these high ones has occurred once. It's just a little bit more randomness there.
But this only impacts you in the boundaries of your data set, correct? More or less?
More or less, depending on the relationship between the buffer size and your data set size. If your buffer size is comparable to your data set size or even larger, I guess you could have, there's really no boundaries at all at that point.
Yeah, yeah. But usually your data set is much, much larger and your buffer size is much smaller, so you can fit in your memory.
Yeah, I mean, that's kind of the point, right? Like using a buffer size larger than the data set size seems kind of pointless.
Yeah.
Okay, so I'm not going to go into this section here. There's a lot of stuff on pre-processing data, some really useful examples here. This one here, tf.example, talks about that tf record proto-buffer format that we saw on the top with the byte strings. Time series windowing, this is a really interesting topic. There's a great notebook over here that TensorFlow produces that shows you not only how to do some time series forecasting pre-processing, the Madrid weather data set I think they're looking at here. I don't remember if it was Madrid or some other location. It's in the Chole book. And
I think it's Vienna, from the German city of Vienna.
Oh, it's Vienna?
Jena.
Oh, okay. Yeah, maybe one could have known that just by looking at the temperatures or something.
It's just there in that file name.
There's some good examples here on data windowing, how to write your own window functions, how to use some of the options within TensorFlow. And then they also show you how to do predictive models as well, using some basic neural networks, convolutional neural networks, recurrent neural networks, etc. I just thought I'd remind folks of the event where we actually went over that in some detail. I based some of the modeling that I showed in this Pedals to the Metal event a couple months ago on these same methods here from the time series forecasting notebook. So if you're interested in us walking through that time series information in more detail, definitely check out this video from April 14th on our YouTube channel. If we go back to the original source here, there's some good information here on resampling. Some information on what you might do if you have a very class imbalanced data set. Credit card fraud being one of the classic examples of that. And a couple different ways that you can sample your data set. Rejection resampling being the one that they go into in some detail here. There's also a couple of bullets at the bottom of the notebook on checkpointing iterators, where you can save the progress of your model, or not just a model, but any iterator within TensorFlow. So if you're iterating over a data set, you can actually use a training checkpoint on that, and it can store where you were, which elements were in the shuffle buffer at any given time, so that you can immediately come back and pick up wherever you left off training. And that's really the content of this notebook here. They just give a full use case example showing a little bit of training at the end. I recognize that we didn't cover much of this in great detail, but it's a really long notebook and just wanted to give you an overview of what all's in it. Before I turn it over to Dimitri, are there any questions on this material?
We appreciate you covering this in not in detail, but going over the overview and the table of contents, for me, that was super useful of figuring out where we are in this novel of a notebook. There's so many
Yeah.
chapters.
Well, what I'm hoping is that people can know where to go,
Yeah.
find the information they need.
I remember that you covered time series windowing and functions in detail in your session, so definitely check that out as well. Cool. Don't see any questions. There are some questions. We think we tried our best to answer them. Yeah, this was super useful. Thank you, Robert. We appreciate it.
Cool. Well, I'll stop my share. Dimitri's got some great content for us. Remember, we're going back to these 3 notebooks in the TensorFlow guide. The one that I just walked through is the tf.data notebook, and Dimitri will be talking about the optimized pipeline performance, and that is going to take us back to this stuff here where we were talking about how to figure out how to optimize what gets run on the CPU and what gets run on the GPU. So without further ado, give the floor to Dimitri.
Awesome.
Okay, let me share my screen. Okay, can you see my screen, guys?
Yes.
Yes.
And just a small comment on batching, actually, or maybe as a segue to this optimization topic. So there is a parameter called drop remainder, right, in the batching. And so I've used it in the past. So what it does is it makes sure that all the batches are the same size. So if you really want your training loop, for example, run really fast, and you have some functional API, etc., so you better define the exact size of the batch, including the batch dimension, so that it doesn't vary from batch to batch. And so that way you mentioned this drop remainder true, and it make sure that all the batches are perfect 2-dimensional, 3-dimensional arrays, all the same size, identical. Let me start by again very quickly revisiting the this page, and yeah, there were. So again, I was just gonna quickly revisit this ETL pipeline. So in the optimization notebook in TensorFlow guide, they actually cover all of these stages. So we will discuss how to optimize the extraction phase by simultaneously reading, through different threads from a single location, or from a collection of files, remote or local. And then we will cover how to optimize the transformation, mainly again by optimizing the mapping transformations. Like if you want to apply some of the custom-made transformations to every batch, how to make that run faster. And finally, the loading stage too. So at the intersection between your extraction transformation and loading. So at the intersection between the CPU or storage environment that you have and the training GPU, accelerators that you have. So what could happen there to speed the things up, including some of the techniques like caching, etc. So all of this will be covered. And let me go to the guide first. So the guide has this nice structure on the right. So we can see what will be covered. So we will go through the naive approach first, when we don't optimize anything, and then we will talk about the prefetching, extraction, transformation, caching, and vectorizing, and then we'll just wrap up with a brief summary of all these good practices. We will not go into reproducing the figures. This is a fairly technical section, So we'll end here also in the interest of time. And just as Robert did, I opened the same page in Colab so that we can run the cells and see what it does, and maybe change some of the parameters. So okay, there we are. And let me close this table of contents just for the sake of the space. Okay. Is the font good enough? Can you see the size?
It's perfect.
Okay, cool. So the topics they discuss are not exactly in the ETL sequence. So first they build this artificial data set. It's very artificial. What it does is basically, it inherits to the tf.data.dataset, and basically, it simulates the opening of the file, so accessing the file that takes time, and they chose 30 milliseconds as a parameter. We can play with this and see how the entire time changes. And so, we can build the generator, the dataset from the generator for arbitrary number of samples. Just for the sake of simplicity, they chose the number 3. So we'll use just 3 samples in the dataset and see how the timing works for those just 3 examples. So first, what we do is we spend 30 milliseconds opening the file, and then we spend 15 milliseconds for reading each sample, so each record from the file. This can be thought as reading each batch. So we're not going to discuss batching, because that would add another layer of complexity, which is not important in this case, because batches can be thought as contiguous blocks of data. So it's the same as just reading one example of one record, basically. And so this is a iterator that spends some time at the beginning and then spends some time actually reading each sequential record or a batch. And then this new method, Dunder method, actually instantiates, so creates this data set and yields the samples from the generator. And so what we will do is we'll take this artificial data set and use it as a example, and we will see how it runs in the naive version without any optimization, and then what we can do to optimize it and cut those times as much as we can. So the training loop is really simple. So we take this data set. So it actually, the benchmark is a custom function they wrote. So it takes the data set. They chose number of epochs 2, and so for 2 epochs, we would read from each. We would read each sample from the data set. We would simulate the training step. So another 10 milliseconds would go to train the model on the sample, and then we will measure the total time, which would be comprised from reading the data set, opening the file, reading the sample, each sample, and then training on each sample. And later on, we will add transforming each sample, so adding some mapping and transformations on top of that. So this is initially how the picture would look, right? So we could, let me see if I have this in memory actually. Yeah. So we could actually run this benchmark artificial data set, and it gives us this number 240 milliseconds for all these 3 stages, right? So the opening, reading each sample, remember, so 2 epochs, right? And 3 samples in the data set. And so opening, reading, and training. And so all of these stages comprise one full epoch. And so basically one epoch, so 2 epochs would run for 0.24 seconds. So this is without any optimization. Now, the first optimization we could do relates to this stage between reading and training. And so it's called prefetching in TensorFlow, and dot prefetch is a method we would apply to the data set. And what it does, it's actually parallelizes these computations. So basically, we could read the data to a buffer which is stored somewhere, but to a temporary buffer, without waiting for the training to finish its job. So the CPU, for example, in this case, if we, if our data lives locally or somewhere else, but not on the accelerator, not on the GPU side, so this part is performed separately on the CPU, and we don't have to wait until our accelerator trains the batch for us to be able to read the next example. So that's basically the entire idea, to collapse these stages and to make it two parallel processes. So we could I'll get back to this auto-tune or prefetch in a second, but the resulting picture is like this, right? So the the CPU, the reading goes continuously. It doesn't wait for the training part, and the training actually follows. And so what it does is, the total time spent on this part, on reading and training, is basically the maximum of the two, not the sum of the two, but the maximum of the two. And so, as I said, we would use dot prefetch. Dot prefetch 3 would mean, give me, so prefetch from the reading from the source, prefetch 3 samples or 3 batches, at the time. There is also a nice parameter called, or I should say, this is probably a global variable in TensorFlow. So they're called tf.data.autotune. And this tf.data.autotune applies to some other optimization stages too. So this is not only for prefetch. What it does is basically lets the system pick the right prefetching parameter itself. And there are pros and cons, right? So if you prefetch too much, you basically, there could be memory problems, and you're actually your processing speed may drop. If you prefetch too little, your training will stay idle for some unnecessary time. So there is a sweet spot in here, and so they introduced this auto tune for the system to actually they use some game theory inspired reinforcement learning technique, actually, as they describe, to actually pick the right parameter.
You mentioned if you prefetch too much, is that the storage hit that you take? Is that the only drawback?
Yes. Yeah. Well, there might be others, but that's the main drawback that they discuss.
Okay.
Because this data lives in buffer somewhere in the memory.
Yeah.
So yeah. And this is already, so this is 200 milliseconds, and here we had 240. So this is already, some economy already here, some savings already here. So now the next thing they discuss is the data extraction, and this is probably the one of the less transparent sections in this notebook, because it heavily depends on specific examples, and actually the TF data guide itself, or TF data, the actually the explanation on the TensorFlow site of this specific function, which is called interleave, is seems to be more informative. But for the sake of consistency, let's go through this notebook. But please refer to the original description of the function on the tf.data website. So what it does is actually it lets you read from a source with multiple processes, like multiple threads or multiple workers reading from the source at the same time, and building this one single data set that then feeds into the rest of the pipeline. And for some reason they use this very artificial example. So the function is called interleave, as I said, and strictly speaking, interleave maps this any function to a another data set. So you have your data set, and then dot interleave parenthesis function, which actually maps it and creates at the same time multiple threads that actually access the mapped data set. And so for some reason they chose to have just an artificial data set of just range 2, right? So dataset.range just creates a range data set. So this is like 0, 1, basically two numbers in the data set, and they apply this artificial data set creation generator, right? So this artificial data set function to each of these elements. So range 2 produces 2 elements. Sorry, range 2 produces 2 elements. Each of those elements get mapped to this artificial data set, and so each of those 2 elements creates another artificial data set. So that's what they decided to choose. And basically what it means is this range 2 is this part, so 0, 1, and then each range 2 gets mapped to artificial data set, and we get this the instances of artificial data set. This seems to be a little bit not transparent, I would say. So if I get rid of the Zoom plague, I'll yeah. So here is the interleave function in the TensorFlow API, and so they discuss a much more sort of natural example consisting of like 4 files and what you can do with this with that. So in the interest of time, let me not go through this. This is pretty transparent here. Like for example, here they have also a range data set, and this is the example of how basically 2 cycles can go through this data set and read them in parallel. And so this is much more I think transparent than the one that they have here. But basically, yeah, go ahead.
To clarify, so when you do this range 2, are you doing the opening part twice? Is that true? You're reading the same file twice?
Yes. Yeah.
Okay.
So for 2 instances, basically, for twice, they do this. They create these instances of artificial data set. So that's what they do.
Mm-hmm.
And so yeah, what we can do is actually the interleave function has this number of parallel calls parameter, which again in this case uses the tf.data autotune, and so it basically what it does is it compresses the extraction part, so the opening the file and reading the samples or the batches. It compresses that into one, because it uses as many parallel threads as needed in this case. And so what you need actually for each of these instances, right, 0 and 1, you don't need to have all of that. So both these processes, so the simple data set and the our artificial data set, this the large data set, they get compressed into one big process, I should say, run in parallel. So that's how it looks, but the sequential nature still remains with respect to this range 2. So this is just run the same process twice and produce this picture.
So Dimitri, one place I've seen this used in the real world is when you have a lot of very, very large TF record files. They will read those with an interleave for performance. That's the only place I can think of I've seen it. Maybe others have seen it. Yeah.
Right. They discussed that in the API on the API webpage. Yeah.
Okay.
So, yeah. So basically, many files, and you want to access them, or many shards. You want to access them simultaneously through multi-threading processes. That's what you use interleave. For some reason, I thought they would use some example like that, because that not difficult to do, but they chose this artificial example.
So that would be the case where you are I/O bound, right? Your bottleneck is reading data from.
Yes. Yeah. So this is this is I/O parallelization. Yeah, that's basically the
Your accelerator is so fast that it can do so many things, but it's staying idle. So that's why you're trying your best to feed it as much data as possible with this I/O optimization.
Yeah. So this is probably in this workbook. This is the only I/O part. All the others are about the transformation and so forth. And this is I/O. Yeah.
It's a good distinction.
So now they get to more sort of transparent part, which is parallelizing data transformation and all kinds of mapping. So they first let me go through what they have. We can parallelize any function that we want to apply to our data set. We may want to, if it could be a domain specific thing, so we could apply any transformation to our images or text or whatever type of files we could have. It could be domain agnostic transformations, right? Such as batching and shuffling and all of that. So it could be arbitrary Python functions, and so if that's the case and you want to apply an arbitrary Python function to your data set, the first thing we need to remember is that TensorFlow doesn't like arbitrary Python functions to be applied everywhere, and so there are cases and contexts that you have to wrap it into special Py function, tf.py function, or have a special decorator tf function that turns your arbitrary Python into graph mode that TensorFlow runs and understands and then could run fast. So like for example, if we do a functional API and we train again a massive data set, the unit of training needs to be wrapped into the train step needs to be wrapped into this decorator to turn it into precompiled sort of computational graph that the TensorFlow understands for it to run fast. And so you can't throw like arbitrary Python functions into there unless you wrap it into this tf.py function. So the same thing applies here. If you have a data set, you have to use this wrapper. And the wrapper they use is, the function they use is just, again, sleep for 30 milliseconds. And this basically simulates, pre-processing of some kind. And then, so if we don't optimize anything and we just apply the mapping sequentially, so this is how it looks, right? So, we open, we read, and after we read each sample or each batch, we apply the map, whatever that is, and only then we can train. So this is without, before any optimization. Yeah, and they call it the naive approach. Now, of course, we can parallelize, right? So we can compress these stages and these stages, and actually the compressed version of this optimized version would look like this. Basically, what we did is here we used artificial dataset .map, and here we used artificial dataset .mapped, and then number of parallel calls equals tf.data autotune. So again, the same thing. So .map accepts this parameter, and when it does, you can have your CPU in this case apply the function through multiple processes at the same time, and so that's a nice gain in productivity you will get here.
Quick question. These functions that you mentioned, you can use any Python function. You just have to use that tf.py function or the decorator.
Any Python function wrapped into tf.py function will do.
So that wrapping is necessary, right? Even if
yes, wrapping is necessary. Yeah.
Okay. And I'm curious how they generated these graphs. I mean, these graphs look great to me, but I don't know how they were.
They have a separate visualization module down there. Yeah. So it's in this notebook. So yeah, caching is another thing. So caching is in this context lies in between transformation and loading. So basically what it does is it loads the data set into memory just once during the first epoch, and then all the other epochs just use the cached data set without going through the entire ETL stages. And so we would apply the cache after .map. So basically we would cache this stage here, right? So the mapped data set gets loaded into the memory, and so all the other epochs. So this is 5 epochs, right? So yeah, this is 5 epochs. So the first epoch actually reads and then processes sequentially, but then everything else, it just trains the existing data set in memory.
Can you choose the caching to happen anywhere? I mean, here you chose it after the mapping, which makes sense.
Yes, you can choose the cache to happen somewhere else. Yeah, cool. And I'll briefly go through the the relative the sequence of this main transformations that you can apply. Yeah.
Why were we spread out there on the training once we've already done the open, read, and map? We don't have to do them again. I would have expected those other bars on the bottom to be on the train part, the second, third, fourth, and fifth epochs. There's still a lot of time there between those other bars. Am I not interpreting this correctly?
Because they didn't, I think they didn't show the.
Yeah. So
right?
Yeah, no, I'm not sure. No, I think this it caches this section. It's basically it has forgotten about the opening, the reading, and everything. So it caches the mapped part, right? So the cache comes after map. So this rows or pinky things are cached. So I don't know why the white blanks here. This may be some overhead related to epoch handling. That's a good question.
Oh, got it. What were you saying, David?
Oh yeah, just a couple of comments. So to your question, George, you see from this graph, right? It's important that you call the cache after you've done your intensive mapping, right? It's sort of at the end, right? So you call cache at the end there, so that you can eliminate all of that. Otherwise, you would have to go back and do the mapping again and again and again, right?
Sure.
The other thing I would say is usually you only apply this to something like a validation data set, not your training data. So this is a little bit confusing, but because you're not gonna be shuffling if you're doing shuffling, which I don't know if we're gonna hit that here, but usually you're shuffling your whole training data set, right, between epochs. And here if you cache it, you'll lose that, right? It'll only shuffle at one time.
Right. So this is what they suggest, and it makes a lot of sense actually. So where to put the cache. So what they suggest is if you have some transformations that require a lot of memory, then do them first. I'm sorry, a lot of time. Do them first, and then cache them, in order not to repeat them. But then, because cache lives in memory, and you may have another, transformation that requires a lot of memory, just to conserve memory, put them after the cache. So that's what they suggest. I don't know if that's, if they use this type of thing in practice. I haven't seen examples, in TensorFlow guide or elsewhere, but this seems to make sense if you are conscious of resources you spend, right?
Interesting. That's interesting. Can you use cache only once? Can you use it multiple times?
That's a good question. I think caching. It just it's implemented on some cache server, right? So Redis or Memcached or something. So it is basically a collection of managed memory, RAM, right? That lives somewhere. So I think the question is, how much resource do you have? And typically those are the expensive parts. So it would depend on the hardware situation.
Yeah, if you mentioned this already, I missed it, but you can also call cache with an argument, right, and pass it if you want to store the data on disk rather than in RAM.
Ooh, interesting.
You can use
Yes,
that if it doesn't fit in memory.
Yeah. So you can cache on disk, and so if you don't mention the argument, cache loads in memory, and if there is a path, so it caches to the path, and again, could save you some time because mapping could be heavy. So that's the caching part. Now they also discuss vectorized mapping, and so the idea of vectorization versus applying the function iteratively to each example is similar to why we do vectorization in general, like in Python or in general in computer science. So it provides big savings and big acceleration in processing speed. And so the way we do basically the vectorization in this context means that you apply your mapping function after you batch the data, not before you batch the data, but after you batch the data. And so they compare the two scenarios. So the first is, you have this data set, you map some increment. So basically, take each element, add 1. And so you map this increment function, and then you batch. And so the picture you get is something like this. So, this mapping is actually mapping each element of your data set, and then goes into training. So that was scalar situation. And the vectorized situation is just, switching the batching and the mapping together. So you first batch and then you map. And then, you basically, your whole mapping, the time is compressed to just one, one operation, because, it allows for this function to be applied as a vectorized function. And so there is quite a lot of time saving. So from 0.62 to 0.2, basically, a huge time saving. Yeah. So that's on the transformation part. And then finally, basically, they discuss some of the things we can do to actually be conscious of the memory and try to reduce the memory. And so I think, they would go into more detail on that in the next guide, which is on profiling and, understanding what happens under the hood and which process spends how much time, etc. So they also discuss here the caching partial computations. As we said, this caching can be done basically at any stage. And just to summarize, so the things we could use is prefetching before training, right? Parallelizing reading the IO stage through multiple threads accessing the files, and then parallelizing the map by this number of parallel calls, and also by using the vectorized functions, so putting them after the batching, not before the batching. Using the cache just to read only for the first epoch, read the data, and read and transform data only for the first epoch, and then use the same data for the remainder of the training process. And then, yes, be conscious of the memory and keep track of, which process uses how much, just to, try to minimize the memory footprint. So these are the summary of the best practices. And then below in this notebook, they go into how to reproduce those figures and, how to visualize these processes. So, but for the interest of time, I think it's better that we skip this part. Okay, so are there any questions in the chat?
Yeah, maybe I missed this, but this reduced memory usage, was there any takeaway except for that map cache map comment?
Not really. Let's read this one more time together. So a number of transformations maintain an internal buffer. If the user defined function passed into the map changes the size of the elements, then the ordering of the map transformation and the transformation that the buffer affects the memory usage. In general, choose the order that results in lower memory footprint unless different ordering is desirable for performance. Yes. So I guess that's generally a good advice. It's just difficult to draw any conclusions unless you see what's happening, and seeing what's happening and which process takes how much memory is covered somewhere else and not in this notebook. So we can't actually visualize that.
Do we see what happens in that analyze performance, the next notebook? Is that the one with the profiling? Does that show us that? I haven't gone through that yet.
Yeah, I think so. Yeah, it
Yeah.
should. Yeah.
Yeah, I was thinking, if you remember from tf.js course, I mean, obviously JavaScript is a much simpler language. I don't know, I consider it much resource oriented than Python. Like, you have to be careful how much memory you use since you're running it on a browser. But there was a specific command that you would delete from memory any unused tensors. I don't know if there's something like that on the actual TensorFlow, full version of TensorFlow, where maybe you don't have anything needed, so maybe you clear it from your memory or cache, like a delete or swap command.
Yeah, you're thinking of the tidy.
Yeah, that tidy that was in tf.js.
Yeah. I think it seems to me that the most of the emphasis that they place is on the CPU side.
Mhm.
So how to be conscious of the memory on the extract transform parts of the data pipeline, and so that may be basically typical set of tools not specific to TensorFlow might also work. So I'm sure there are many tools to monitor which process takes how much memory on your traditional CPU side, because GPUs, I think they cover that separately as part of their optimization. So
Nice. Awesome. This was very useful. Thank you, Dimitri. And as you mentioned, there is a specific section that describes how these graphics are generated.
yeah, it's below here. So a bunch of draw timeline and so this basically draws this entire process.
Nice. Cool.
Okay, let me stop sharing.
Anybody has any questions, feel free to add them or unmute yourself.
Yes. Can you hear me? Is Vladimir here? Maybe I can turn on my. Can you hear me?
I hear you very well.
Yeah.
Yeah.
There is an echo somewhere.
So are we going?
There is an echo somewhere.
Yes, I think that's yeah. Is the echo still present? No.
Sounds good.
No. Okay. So are we going to discuss this analyze pipeline performance article that actually Robert commented? So this is the next one on the yes. I mean, if we're going to discuss, maybe that's there is.
I can't open
If
the.
we're not going to discuss it, I think it will be.
I can bring it up if I go back to share.
If it's not.
Yes, please do. Yes, please do.
Actually, or I can share my screen if you want. If you let me share my screen.
Robert is doing it.
Let me try.
This is the notebook you're talking about, right? Analyze.
Yes. Yeah. Analyze performance. Pipeline performance. If we're not going to discuss it, I think it will be good to say a couple of things.
Well, I was hoping that one of us was going to take that next week.
Okay. All right.
It's not technically part of the course, though, so we might not.
Well, okay. So we have maybe a couple of minutes. So if you want, I want to say something about it, because the two both presentations today were too clear, and I think it's time to introduce some confusion. It will be good for the, it's good to have some randomness in the data.
Did you want to share something?
Yes, my screen, if you want. So I can share my screen. I selected, I don't know, do you see something? Do you see my screen now?
Yes. Yes.
Yeah, so this is the Analyze Pipeline Performance link. I strongly recommend reading the whole article. But we don't have time, and actually it's not, I just want to make one point. So TF profiler, so this is, these figures here that you see below, they are all captured with Tensorboard, and more specifically with the plugin which is called Profiler in Tensorboard. There is some quirks there because the profile, it looks like, works only with CUDA 10.2 and above. So if you try it yourself on your GPU, you need, I have done it with 11.0. Otherwise, you cannot see it. Okay, so the point that I'd like to make, so this is 4, just bottleneck analysis. So I am going to show, so this is this figure here, I just put it large so you can see. So this is what happens specifically on the CPU. It gives you the threads both on the CPU and the GPU. Currently, the GPU is not important. Everything happens on the CPU, and this gives you, this one is one thread. So all these functions are called within this thread. So the function that you see here is actually what happens on the graph. This is not the name of the function that you see in the Python code. So it's kind of not straightforward, but it's clear enough to understand the sequence of execution of different functions that we saw in the presentations, especially this parallelization part. So they talk about upstream and downstream. So what is important? So you have this, just note the execution. So you start the batch function. This is batch. Then you repeat. Then you map, and finally range. So this is the start of executions. Then first the range function finishes. Then the map. Then the repeat, and then batch actually continues because you spend several things. Now, if you go here and you see the code that actually corresponds to this, you notice the following: the range is on the first line, whereas its execution starts last. The map, which is in this case just a dummy function, is the second one that you have requested, and it starts to get executed before range. The repeat is here, so this is finite repeat because you have only 2, and the batch is the first one that starts execute, whereas it is the last one. So the point is the order in which these functions that you see as lines of code is different from. So the order of the function calls in the Python code is different from the way they're executed, their execution started in the actual on the actual CPU. So that's a point number 1. Point number 2 is they talk about synchronous and asynchronous transformations. So these functions, batch, map, prefetch. So let's say first batch and map. They call them synchronous because they're running the same thread as the other ones. So all these things here, this is only a single thread. I think you better read also for this tf.data.dataset get next. There is discussion about this, what exactly means and what thread is this about. But the point is there are 2 types of transformation: synchronous, so the batch, and the map, which are not which are not called with number of calls equal to 1, 2, 3 or something like this. They're just the synchronous batch and map. And there is also asynchronous transformation that are spawned, that are put in another thread that is spawned as a result of code like this. So there's a prefetch parallel map. So number of parallel calls, I think 2 and above, parallel interleave, and there is also even map and batch. So, okay, I'm going to open this here again. So this is another example in which there, in addition to what we saw before, this map, things like this, we also have a prefetch. And the prefetch is actually started before everything else. So when you look at the code that corresponds to it here underneath, so you see the same thing. So range, map, repeat, batch, and prefetch once. Compare here, just prefetch is added. So what happens is, oh, sorry, I put it on different thing, that's fine. So what happens here is that this is the thread in which the prefetch starts first. And then you start the rest of the code, which is the batch, the repeat, the map, and the range. So when you look at the, so when you look at code
Wazir,
like
can I ask a question? So
Wazir, can I ask a question? Yes, yes.
So when you say start first, do you mean visually on the screen, or is it like as a process starts first?
Or is it like as a process starts first? As a process. So these traces here, actually specifically this one for us, I think. Okay, let's do this first because it's clear. So this here is the timestamp on the CPU. So this is microseconds, 58. So so with the TensorBoard, you basically have a snapshot of certain interval what happens in the actual CPU, and this is provided by the TensorBoard Profiler. So when you look at this, when you start it, you can measure these times. You can measure the duration of this. There is a very good kind of GUI tool for profiling. So the execution of, let's say, finite repeat starts around second 58, 92 microseconds and continues to 58, 924. It's like 4 microseconds in duration. And the map, which technically you have requested to be second in execution. Starts before repeat. So this is repeat here. So this is the repeat, and this is the map. So see how the code goes. First you say I want to map, and I want to repeat. But the execution is actually bottom up. So you start first the batching function starts, then repeat, then map, and then the end of range. So create this. So first is the batch. Ignore this do compute. First is the batch, then the repeat, then the map, and finally range. First range finishes, then map finishes, then repeat finishes, and batch continues because you have several things. So this is in the same thread. And if you do it, if you also have a prefetch, you see that the prefetch actually runs in a separate thread. That's a separate thread. And these are the threads of TensorFlow, because you have also thread of Python, in which you have these eager executions. So I think actually I struggled quite a bit with this to install TensorBoard if you haven't, and to put the profiler. I think for these kind of things you don't need a GPU because there is no GPU here. This is everything happens on the CPU. So I hope it won't complain. But this is, you need a profiler. That's one of the tools, the plugins of TensorBoard. And then you can actually study the executions of a pipeline. And if you have a GPU, here comes another thread here on, actually not another section which has device GPU or something like this. And there you can see the major threads that happen on the GPU. And then you can relate the pipelining on the CPU and how the data is fed with the time when the actual training, let's say the ADAM algorithm or whatever optimization algorithm, starts and finishes on the GPU. So when you try to get high performance, what I'm running now, the goal is to overlap pretty much the GPU execution with the CPU data pumping. that's kind of my current goal. And I think there is, um, I think I see somewhere a kind of good screenshot of a TensorBoard about that. But if you really need high performance data input without seeing what happens inside, I think it will be very difficult to design the pipeline. Uh, Specifically for what I started explaining, that the order in which these kind of functions are called and executed is not how the code is written. And in part that's let's say illogical to be, because the idea of TensorFlow graph computation graph is to find out to reorder the execution of the functions of the executions of the execution of the functions as to maximize the performance. That's kind of my explanation.
Thank you. Thank you, Vladimir. We appreciate it. Yeah,
Okay.
yeah. We hope to cover this in detail next week, but thank you for the preview and the highlights that you mentioned.
Okay, so I'm going just to post I will just post in the chat this link,
Sure.
this analytical whatever. No, analyze pipeline performance. That's look at the story.
Sounds great. Thank you, Vladimir.
Yeah, so you're welcome. I just want to shut down my screen.
You don't mind
Sharing.
muting yourself, because I still hear an echo. Perfect. Thank you. Robert, do you want to tell us about this? Go ahead, Vladimir.
Yeah, I'm trying to stop sharing.
Yep, you stop sharing. We can see everybody now. You're good. Robert, you want to say a few words about next week? And again, thank you, Robert, and thank you, Dimitri, for your great sessions and presentation. Thank you, Vladimir, for the preview for next week as well.
Oh, okay, sure. So next week we'll be running through this notebook that Vladimir just previewed for us on Analyze Pipeline Performance. It's a great follow-on. Shows a little bit of profiling that we just got a taste of, and then we'll also cover the optional unit from course 3, week 4 in the Coursera course on publishing your datasets to TFDS. So if you have data that you think might be a good fit for the TFDS ecosystem, there's a way to, I guess, send some kind of pull request for that. I'm not familiar with the process yet myself, so I'll have to go through the course.
Mm-hmm. Is there any mention of Tensorboard? I know Tensorboard Profiler was there, but is there any mention of how do you actually use Tensorboard?
I believe Tensorboard is in course 4, so we'll get to that in a couple weeks.
Yeah, it's in the next one.
Good one. And just to clarify,
as is TensorFlow Hub.
Right. For everyone following us, course 3, week 4, the material is very close to what Dimitri covered today, right, Robert?
Yeah, the main part of course 3, week 4 is this optimization of pipelines.
Got it. Okay, perfect. So yeah, we'll definitely go over that, but it's basically what Dimitri covered today in terms of content. Great. Cool, friends. This was really interesting. Thank you, everyone. Thank you, Robert. Thank you, Dimitri. Thanks, Vladimir. Thank you, David. Very interesting session. Yep, let's discuss offline who is covering what for next week, and that should be a good wrap up.
Thank you, George. Thank you, everyone, for attending.
Thank you. Thanks,
Thank you, everyone.
Have a great night.
Have a great night. I'll stop the recording here, and if you want to hang out, hang out. Otherwise, I'll see you next week. Thank you for joining us on YouTube. Thanks again, and feel free to subscribe and like our videos.